Hi, this is Mrs. Basin, and in this screencast we're going to work through some buffer calculation problems. So our first problem is just asking what the pH of a buffer solution is. We know this is a buffer solution because we have a weak base and the salt of that weak base, which serves as our conjugate acid. The other type of buffer you could have is you could have a weak acid with a salt, which would then serve as the conjugate base. So while we're looking at this, I'm going to go ahead and label this. So NH3, the ammonia serves as our weak base, and then this NH4NO3 serves as our conjugate acid. To figure out or calculate the pH of a buffer solution, there are two ways you can go about this. One is you can use an ice table, and then once you set that ice table up, you can calculate the pH from either the OH minus, if you have that at the end, like you would in this particular problem, or the H plus, if this was an acid buffer. The way I like to do these is to use the Henderson-Hasselbalch equation. So that, again, is pH equals pKa plus log base over acid. Now in class we also looked at another version of this where we had the POH equals the PKB plus log acid over base, but I'm going to use this one, that way we can consistently use the same thing, so we maybe try to avoid some confusion. So for this, I'm solving for pH. I need the pKa, and then I already have my concentration of base and acid from up here. So to get the pKa, I'm going to take, and I'm going to do a little side calculation down here, pKa again is the negative log of the Ka. Now for this particular problem, because this is a base, they don't give me the Ka, they give me the Kb. So if you remember from before, Ka times Kb equals Kw, which was 1 times 10 to the negative 14th. So if I plug that value in here, I have Ka equals 1 times 10 to the 14th divided by my Kb, which was given up here. So 1 times 10 to the negative 14th divided by 1.8 times 10 to the negative 5th. That gives me a Ka value of 5.6 times 10 to the negative 10th. And then if I plug that in down here, I end up with a pKa value of 9.25. So I'm going to go ahead and go back to my equation. So pH equals pKa, which I just solved for, 9.25, plus log base over acid. Base, again, comes from here, so 0.30 molar. And this, when you plug it into this equation, these have to be in molarity. They have to be in molar concentration. So 0.30 was my base, and then my acid, again, was up here, 0.15. Then I work through that, and I solve all of that. My pH comes out to be 9.56. And again, that makes sense because it's slightly basic, and this is a basic buffer. Okay, my next buffer question is, again, this is a buffer solution. It has 0.2 molar HCHO2 and 0.3 molar NaCHO2. It gives me the volume of the solution, and it also gives me the Ka. So this is a three-part problem where it's going to first start out asking what is the initial pH of the buffer, and then how does the pH change when we add either a strong acid or a strong base to it. So this problem will carry on through the next 3 slides. So this one, again, is going to be very similar to that last problem that I just did. The difference is this is now an acid buffer, so here's my weak acid. So I'm going to go ahead and label that acid, the top. And then this is my salt, which serves as my conjugate base. They tell me how much I have. I don't need that for this particular problem, but I will need that in the next 2 parts of this problem. And then they also give me the Ka value. So again, I'm going to do my Henderson-Hasselbalch. pH equals pKa plus log base over acid. Okay, so my pKa again is negative log of the Ka. So I don't have to add that extra step in this time because it's already an acid. It already gives me the Ka. Ka is 1.8 times 10 to the negative 4th. So my pKa in this situation is 3.74. So I can go back over to my problem here. pH equals 3.74 plus log base. Here's my base, right here. So that's already in molarity again, so 0.30 molar over acid, which is up here, 0.20 molar. So when I solve for that, my initial pH of this buffer is 3.92. And again, that makes sense, slightly acidic, and this is a buffer made out of a weak acid. So now, in the next two slides, we're going to look at what we're going to look at here then is what happens when we add an acid or a base to the buffer. So just as a reminder, a buffer again is a substance that resists a change in pH. So when we have a buffer, it has two components. It has an acid component to react when base is added, and it has a base component to react when acid is added. So before we set up our before change after table, let's go ahead and look at the overall equilibrium of the buffer. So there's our HCHO2, and that's dissociating into H plus and CHO2 minus. And so we can label this, we can see what's what. This is our acid component here, and then over here, this is our base component. So when we set up our BCA table, what we have to figure out is which component of the buffer is reacting with what's added. So in this case, we're adding NaOH. So we're adding a strong base, so that means that the acid component is what's going to react with that to use up that OH, again, resisting the change in pH. So when I set up my before change after table, I'm going to start with my acid, HCHO2, and I'm going to add my OH minus, because that's what's going to be reacting, and then what we end up with is my CHO2 minus, and then my other substance I get then is water, because the OH is going to pull the H off, and that's going to generate water. Now we can add water to the table here if you want, but you don't necessarily have to, because we know that that's not something we're going to worry about calculating. So the other difference here, when we have our BCA table, is it has to be in moles. So unlike an ice table where everything has to be in molarities, or when you're using the Henderson-Hasselbalch, it has to be in molarities, BCA table before change after tables has to be in moles. So to fill all this out, we have to do a few calculations here. So the first thing we want to know is how many moles of our acid do we have. So that's where we need our milliliters and our molarity of our acid. So down here I have 0.125 liters. I went ahead and changed that milliliters to liters before I put into the calculation, and it's 0.2 moles per 1 liter. Okay, so that gives me 0.025 moles. So that goes right here, 0.025 moles. Okay, my next blank here is my OH minus. So I have 50 milliliters of 0.1 molar NaOH. So 0.050, change it to liters, 0.1 mole per liter. And that gives me 0.005 moles. 0.005 moles of OH minus. And then my last one, let me change color here so I can keep track of what's going on, is my CHO. So I have 0.3 molars, and I still have 125 milliliters. So 0.125 again, liters. And I have 0.3 moles per liter. And that gives me 0.0375 moles. 7.75 moles. Okay, so now I'm ready to go ahead and do my calculations with my table here. So the OH minus is going to get used up, so I'm going to subtract that. So I end up with 0 left. It's going to react with HCHO2, so I'm going to subtract it from there also. And that leaves me 0.02 moles of acid left. On the product side, I'm going to add that 0.005. Because as that H gets pulled off, it's going to generate CHO2 minus. So I end up with 0.0425 moles of that. Okay, now before I can do anything else, before I can move on here, I have to change all of these back to molarities. So what I have to do now is, divide all of my moles by my new volume. So my new volume, I had 125 milliliters of buffer, and I added 50 milliliters of base to that. So that is 0.175 liters, or 175 milliliters of new solution. So that's what I have to use when I calculate my molarities. So that ends up being 0.11 molar acid and 0.24 molar base. Okay, so again, let's label this base, and this is acid. Now at this point, what I can do is take these into an ice table, or I can use the Henderson-Hasselbalch to find out how my pH changed. I'm going to use the Henderson-Hasselbalch just because I think it's a little bit faster here. So pH equals pKa plus log base over acid. So pKa I have from the previous problem, so it's still 3.74, plus log base, which is my 0.24 from right here, over acid, which is 0.11 from there. So when I solve that, my pH ends up being 4.08. And if I look back to what my previous pH was, the pH of this buffer started out at 3.92. So when I added that 0.1 molar strong base solution to it, that did a pretty good job of resisting the pH. It is a little more basic, which makes sense because I added a base to it, but not by much. Okay, so now in our next one, what we're going to do is look at what happens if we add an acid to the buffer. Okay, so I'm still going to go back here and show my original dissociation so we can keep track of what's going on. HCHO2, that dissociates into H plus, CHO2 minus, and this time I'm adding H plus. Okay, so this time it's going to react with the other part of the buffer. It's going to react with the conjugate base part of the buffer. So when I set up my before change after this time, I'm going to start with my CHO2 minus. That's going to react with the H plus that I'm adding, which is going to give me HCHO2. Just like before, when I set this up, I have to change everything to moles. Now my moles of base and acid I still have from the previous problem. I just have to make sure I put them in the right place. So I'm going to use those values instead of recalculating. I'm going to use those from the previous problem. So my moles of base that I had is 0.0375. And again, that was calculated using 125 milliliters of the 0.3 molar NaCHO2. My moles of acid, again from the previous problem, was 0.025. calculated from 125 milliliters of the 0.2 molar. My H plus, I have 0.050 liters of 0.1 molar HCl, so that gives me 0.005 moles. So that goes right here. Okay, I'm going to switch colors again. So now, just like before, the H plus is what's going to get used up, so we're going to subtract that. So that all gets used up. It's reacting with the CHO2, so we're subtracting it from there also. So I end up with 0.0325. And then it gets added to the other side because it's forming HCHO2. So I'm adding the 0.005 here. That gives me 0.03. Again, just like in my last problem, before I can do anything with this, I have to convert these back to molarity using my new volume. And again, my new volume is still 50 milliliters of strong acid added to my 125 milliliters of buffer. So that's 0.175 liters. So that gives me 0.186 molar. And that's my base first this time. And then that gives me 0.171 for my acid concentration. Again, you can take those now, put them into an ice table, and calculate your H plus from there. I like to use Henderson-Hasselbalch, so that's what I'm going to do here. So pH equals pKa plus log base over acid. pKa, same from other problem, still the same acid, 3.74, plus log base, 0.186, over acid, 0.171. Running out of room down here at the bottom. Okay, so pH calculation goes to 3.78. And again, if we think about that, our original was 3.92, so it decreased a little bit, but for the most part maintained the pH, didn't allow a huge change in pH. It became a little more acidic, which makes sense because we added a strong acid to it.